Hello students. So let us continue our frequency domain analysis of transmission lines. So in this particular case, we assume that the excitation is of a single frequency, right? So let us briefly look at the idea or concept of phasors, which was probably introduced to you earlier in the electronics and electrical circuits course. So you can always go back to those lectures and have a refresher, but I will also do a very brief introduction to the notion of phasors, because we are going to use this in order to look at frequency domain behavior of transmission lines. For a change, it's going to be the frequency behavior in steady state, right? So we'll see why. So phasors is essentially just a complex number, right? So all of this stems from some very beautiful mathematical relations. The first of it being the Eulers relation, right? Which essentially says that e to the j theta, we try to avoid using I for square root of -1 because it might be confusing with the notation for current, right? So we'll just say that e to the j theta, where j stands for square root of -1, is equal to cosine of theta plus j sine of theta, right? So this is a very elegant mathematical expression which relates, which shows a relationship between the numbers shown in magnitude and phase and the real and imaginary components, right? Sort of the rectangular coordinates to the r theta form, right? So you can also think of this as being 1 times e to the j theta is cosine of theta plus j sine theta, right? So in the complex plane, you can sort of indicate this, right, where the magnitude is 1 and you have a angle subtended by the line joining the complex number to the origin, and the angle it subtends to the horizontal axis, right? So this is the first relationship that we'd like to borrow. The second interesting thing, the mathematical relation, is when you have linear operators, right? So for a linear system, we say that when the system is excited by a particular frequency omega, that no new frequencies are generated, right? So even the outputs that are generated by the system have the same frequency omega as the input excitation, and no new frequencies are generated. This is true for any linear system, and since we are looking at transmission lines, which is mostly modeled with components like resistors, inductors and capacitors, which are all linear elements, we can say that this condition that we see can be applicable for the case of studying transmission lines in the frequency domain, right? So we say that for a linear system, when I excite the input at omega, I also say that the output contains only the frequency omega, right? Now there can be phase shifts, right? So between the input and output, so for example, you can take a simple RC circuit and maybe compare the current flowing through the capacitor as opposed to the voltage of the excitation to the RC circuit, and you will notice that the capacitor, the voltage across the capacitor or the current through the capacitor also has a sinusoidal form, right, for the current or voltage, given that the source excitation is also sinusoidal and it is at the same frequency, right. And the only difference being that either the current leads the voltage for the case of a capacitor, or the current lags the voltage for the case of the inductor, right. These were also what we saw with the toy models for inductors and capacitor early in this course, right. We also see a very useful relationship where if I were to take, say, the derivative of e to the j omega t, I essentially get j omega times e to the j omega t, right. So, of course, I can even have some constant in front of this e to the j omega, in which case, right, I would just have that. So, now the derivative, right, is actually yielding the same function on which it is operating with, and it's only multiplied by a scalar, right, in the front. So, this is a very useful feature where if I can call this function y, dy by dt is essentially some scalar, let us say y tilde times y, right, where this y tilde is essentially j omega in the case shown above, right. So, y is a e to the j omega t. You essentially just have the derivative now being proportional to the function itself, right, and this will be true even for integrations. So, if you remember or recall that the telegraphs equations that we derived for the transmission line, they were basically differential equations, where you either had to do differentiation or integration. So, for both of these two operators, we noticed that the function e to the j omega t conveniently falls out, right, as the function itself with only a pre-multiplied scalar, right. So, these are some mathematical relations that we would like to exploit, that when you send exponential functions through derivatives or integrals, you get back the same function only scaled by a prefactor, right, and this prefactor can be complex. Okay. So, with these mathematical relations in mind, we are going to say that no matter whatever be the electrical circuit to which I am, say, forcing a particular voltage or current, right, at some frequency omega with an excitation that goes as a cos omega t, that I can say that whatever output response, be it a voltage across a particular element or a current through a certain element, will always have a form, a functional form, where you can notice that the constant in front of the cosine has changed. We allow for changes in the scale. I mean, this is of course true, because if the input excitation was voltage and the output that I am seeking is current, of course A and B, right, have different units itself, right. So, we have to allow for changes in the prefactor, right, and we only allow for a change in a constant phase, right, phase relationship, but the time dependence, right, is only dictated by the same frequency omega that forced the linear system at the input, right. So, in some sense, I can characterize the response of any linear system by knowing values for b over a and phi, right. So, it is essentially just two variables. Okay. So, a more elegant way to kind of keep track of these two variables, right, is perhaps to explore the Euler's relationship and saying that a cos omega t is really the real part of okay, the real part of a tilde e to the j omega t, where a tilde is essentially a, right. So, you use the Euler's relation for e to the j omega t, you can write that as cosine of omega t plus j sine of omega t, and if you were to look at just the real part, you get the cosine function, right. And in the output, you can write it as the real part of b tilde e to the j omega t, right, where now b tilde is essentially b e to the j phi. Okay. So, you can substitute for b tilde as b e to the j phi, and you will notice that e to the j omega t multiplied with e to the j phi can be added up to get a single argument omega t plus phi, and you will notice that if you take the real part of that, you will get the output that I have shown, right. So, now this b tilde is essentially what we call as a phasor. It is a complex number, right. Although the input comfortably has been chosen to be a real scalar, right, the output in general is allowed to be a complex scalar b tilde, which is what we call a phasor, right. So, this complex plane notation, where say I have a real value for a, right, and then I can have some arbitrary right, we can have an arbitrary complex number to signify the difference in phase, right. Remember that since a and b are varying in time by the same prefactor omega, right, the frequency, in the reference frame of something that is spinning around, right, with omega, I can kind of say that a and b are stationary, right. So, in a reference frame, so if I were to look at plotting the entire phase omega t plus phi, that would essentially be changing over time, right, and it will be spinning around with a rate of omega. But if I were to look at this in the reference frame of a, right, which is also spinning around in the same direction with a rate omega, uh, the phasor B, right, will look stationary compared to phasor A, right. So, the phasor notation is highly beneficial where we have functions that are oscillating at the same frequency, but merely have phase differences between them, right. So, it is a very convenient notation, and this is how perhaps in your prior courses also you might have been given the idea of currents leading or lagging behind voltages, right. So, So, I hope this brief introduction to phasors uh, is sufficient, and I also encourage you to go back to prior lectures and prior courses to refresh your phasors, right.